Okay, on this video we are going to see the cooling and warming Newton's model differential equation. And to do so, I'm going to show two examples. Here we have hot tea, and here we have a cold beer. What I'm going to do is to plot against the time how the behavior of the temperature in the hot tea and in the cold beer behaves. Okay, so let's start with the hot tea. We are going to assume that it was boiling. It was boiling the tea. So when the tea is served, then the initial temperature will be something around 100 degrees Celsius. Okay. So what will happen after the hot tea is prepared? Well, the temperature is going to decrease. It's going to start cooling. So let's do the plot of this behavior. So this is the time, and this is t as a function of time. So the x-axis is the time, and the y-axis is the temperature. So when it is prepared, then it is around 100 degrees Celsius. Okay, so that is the initial point. Okay, so what is going to happen? Okay, as the time goes on, then this temperature is going to decrease. But how much is going to decrease? Now, is it going to be equal to 0 degrees? Well, not. No, as you may know, the limit temperature is not 0 degrees. That should not happen. Okay, so what is the limit? The limit of cooling. Well, the limit is actually something that is the T ambient, the ambient temperature. So what will happen is that there will be a heat transfer. The T is going to lose heat with the surrounding environment. And the surrounding environment is going to have something that is T ambient temperature. So that is the limit. So assume that we have a T ambient somewhere like here, 20 degrees or 25 degrees depending on the day. The ambient temperature changes through the time, but let's assume that in a short period of time the ambient temperature remains constant. So what will happen here is that it's going to decrease, it's going to decay, it's going to cool, but the limit will be the ambient temperature, right? So we have like an horizontal asymptote, and that is the limit. It cannot go below because the heat transfer law doesn't allow to go to be cooler. Okay, so that is the model. Okay, now what will happen with a cold beer? Let's assume that a cold beer that you take from the freezer is going to have like very cold. Let's say that it's going to be like close to 0 degrees, right? Or maybe 1 or 2 degrees. Okay, so if I make a plot of that, the time and the temperature, different temperature, I'm going to use, say, temperature of the beer as a function of time, and this to be the temperature of the coffee, or the tea, sorry. Well, it doesn't matter, it's the same. So the temperature of the beer, so because it's going to be cold, and let's assume that you have a T ambient somewhere here, T ambient. So what is going to happen is if you take the beer out of the freezer, then the beer is going to warm. So you have a cooling and then you have a warming. Let's assume that your initial temperature is somewhere like 1 degree. Okay, let's say that it is 1 degree Celsius, somewhere here. Okay, so what is going to happen is that it's going to start warming, but it's not going to go above the ambient temperature. All right. So what is going to happen is that now the beer is going to get the temperature from the environment. So here again we have an ambient temperature of the environment. So the heat is going to be transferred from the environment to the beer, while here in the cooling, the, the cup of tea is going to transfer the heat to the environment. All right. So, but in the end, it's the same limit. You cannot go above the ambient temperature because of the heat transfer rules. All right. So what happens here is that you have this is the cooling example, and this is the warming example. What we are going to do is what Newton's did. Try to make a model, differential equation model, out of this behavior and this behavior. And what Newton realized was the cooling, or let me write it, the Newton's model is that the cooling or warming speed or rate is proportional to the difference between the current temperature and the ambient temperature. So what Newton's proposed was, okay, if the difference between the temperature and the TMN is big, then it's going to fall faster or increase faster. But once it is close to the TMN, then the rate or the speed is going to be slower. So the closer you are to the TMN, the slower the heat transfer. But if the difference between the cup of the tea temperature and the TMN is big, then the decrease is going to be faster. In the same for the warming. So let me remark here rate, which is speed, rate of temperature. So that means the rate of the temperature is the derivative of the temperature with respect to the time. Remember that the derivative is the speed or velocity. And it says is proportional. Proportional, okay, so we have a K to the difference between the current temperature and the ambient temperature. So here is a difference with the population model. So it is a delta between the temperature, T of T, minus the T ambient. Okay? So this is the differential equation model. Now, why we also have a proportionality here? Well, we have a proportionality because this proportionality depends on the heat transfer variables. For example, it is not the same to have a cup of tea or having what you call we usually call the what is the name of this? Well, the material here is different. Okay, so the heat transfer could be different from this heat transfer depending on the material that is covering the liquids. Okay, so the heat transfer could be different, the heat transfer rate could be different, and that is why the proportionality. Okay, so because this is the model, Newton's model, let's solve the differential equation. Again, you don't have to solve every time the differential equation, you can just work with a final solution for the problems. Okay, so again, this is a variable separable differential equation in this way. So I'm going to take the differential of the temperature divided by this as a division, T of T minus T ambient equal to K differential of T. And because it is a variable separable differential equation, we can apply the integrals, okay? So what happens here is that the T ambient is a constant, so you don't have to worry about this. So this integral happens to be the natural lorem. The natural lorem of T of T minus T ambient equal to the integral of this is just Kt plus the constant. Okay, so in order to clear the temperature, we have to apply exponentials on both sides. Okay, if you apply exponentials on both sides, then this and this cancel, so what you have is T of T minus T ambient equal to the exponential of Kt plus the constant, but I'm going to write like this, exponential of the constant, which is the same. Now, exponential of a constant is still a constant, right? So the t of t is equal to this to the other side, the constant exponential of kt plus the ambient. And this is the model solution. Okay, so on the next video we are going to do an example on how to apply, to personalize. Well, this is the general model for this behavior, all right? In the next problem we are going to do a specific, personalized problem, all right? Now, this covers either cooling or either warming, okay? So see you in the next video.